In this video, we're going to talk about exponential functions. So this is a special type of function where the power of x, the variable x is in the exponent of your function. Okay, so when we're dealing with polynomials and all the functions that we've had in the past, if we've had an exponent, there has not been a variable in it. It's only been a number. Okay, so let's just remind ourselves, okay, we know how to do integer powers. So for instance, 2 cubed is 2 times 2 times 2, so 3 times, which is going to give us 8. Okay, fractional powers, so if I had 2 to the 1/2, I know that's root 2, because if x equals 2 to the 1/2, then I could square both sides, which would give me x squared is equal to 2. And I want the positive number because it has to be a positive, so that's why it satisfies that equation. But the fractional powers give us roots. So remember that if we have 2 to the m over n, that it's the nth root of 2 to the power m. Okay, or you could write it as the nth root of 2 all to the power m. Okay, those are the same thing. Now, what about if we wanted 2 to the pi? Okay, pi is an irrational number, so it's an infinite, non-repeating decimal, so 3.14159, blah, 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 blah. So 2 to the pi, we could approximate by just taking the exponent closer and closer to pi, so including more and more decimal places. And what we get is going to get closer and closer to what 2 to the pi is. So what that means is 2 to the x can be defined for any real number x. Okay, so it doesn't matter if it's an integer or a fraction or even an irrational number. Okay, so we can talk about 2 to that power. So just to remind you, the exponent rules are going to be extremely important in this section and from now on. So we want to remind ourselves how to use exponents. So if a and b are positive numbers, a to the x times a to the y is going to be a to the x plus y, so we add the exponents. If we have a times y all to the power x, that's a to the power x times b to the power x. A to the power x all to the power y is a to the power x times y in the exponent. If you have division with the same base, maybe I should write that. So just notice here that they're both base a. Okay, also here, same base. Okay, so a to the x divided by a to the y is a to the x minus y. A to the minus x is the same as 1 over a to the positive x. And anything to the power 0 is always 1. Okay, so these are the most important exponent rules, and they're going to be extremely useful going forward. So what is an exponential function? Okay, so an exponential function is obviously a function of the form, so let's call it f of x, and it's going to be c times a to the power x. Okay, where a is bigger than 0 and not equal to 1. Okay, and a real number. Okay, and c is also a real number, but that isn't 0. Okay, so that's the form that they're going to look like. Oops. Okay, now A is known as the growth factor Okay, and C is known as the initial value. Okay, so that's some other terminologies. But they all have the form C, a constant, times a to the power x. So the important thing to note here is that x is in the exponent. Okay, now the reason why we want, so a being bigger to 0 maybe isn't totally surprising, but why do we want to get rid of the 1? Because if this is a 1 to the power anything is always 1. So then we would get a constant function, and a constant function behaves very different than an exponential function. Okay, so you would just, in order to sort of get rid of that case, that's why we want to get rid of the a equals 1. We need a bigger than 0 so that we can have fractional exponents. Because if x is 1/2, I can't have a negative number here because then it's going to be the square root of that number, which obviously doesn't exist. Okay, so that gets rid of those problems, and the a equals 1 just gets rid of that constant function, which is different than what we want. So with those conditions, the domain of any exponential function is all real numbers. So it's negative infinity to infinity. Okay, or all real numbers. So you can have a to any power. Okay, it doesn't matter what you plug in. So let's look at the graph of one of these. Okay, so I'm going to do y equals 2 to the x. Okay, now if you want, you can make a table of values. Maybe I'll do that on the side here. Okay, so if it's 0, then it's 2 to the 0, which is a 1. So I get a point at 0, 1. If x equals 1, then it's 2 to the 1, which is 2. Okay, if x equals 2, then it's 2 squared, which is 4. Okay, if x is 3, then it's 2 to the 3, which is 8. Okay, so it's way up here. So you can see it's growing very quickly. And what with the pandemic going on, you've probably seen these type of shapes quite a lot. Okay, so it's growing quickly. This is an exponential function. Now, what if we put in negative numbers? So if I tried negative 1, 2 to the minus 1 is actually 1 over 2 to the positive 1. So at negative 1, it's actually at 1/2. Okay, if I did negative 2, 2 to the minus 2 is 1 over 2 squared, which is 1 over 4. So that's going to be even smaller. And in fact, you're going to have a horizontal asymptote at this side at y equals 0. So it's going to approach y equals 0 as the x values go to minus infinity. So you're going to have a shape, oops, like that. And we're going to get closer and closer to 0, but never cross. Okay, so so I should label some of these maybe. Okay, and then we have negative 1 and 1/2, and I'll stop there. So that's what our graph of 2 to the x looks like. Now I'm going to leave you the graph of 1/3 to the power x, but I will say that you could graph it by graphing 3 to the minus x, because those are actually equivalent. Okay, so maybe I'll put in an extra step there. But 1/3 is 3 to the minus 1, right? And then if you have 3 to a power, you multiply those powers. And you could think about this as a transformation. Of y equals 3 to the x. Okay, you don't have to, but you could. Or you could just do a table of values and do 1/3 to the x. Okay, but I'm going to leave that one for you. So, in general, for base A, bigger than 0 and not equal to 1, the range of these things is always going to be 0 to infinity. Okay, so y strictly bigger than 0. They don't have x-intercepts. Okay, so there's no x-intercepts. The y-intercept is always at 0, 1 because, so this is, I guess I should say, for the function like this, where the c value is 1. So this is since a to the 0 is always equal to 1 for any a. Now, if a is bigger than 1, like the one that we drew, the 2 to the x, then f of x is going to be always increasing. Okay, but if a is between 0 and 1, like you're going to do for your other one, the 1/3 to the x, then it's going to be always decreasing. Okay, so that should be a hint for you. So your graph should be always decreasing. And like I mentioned, there's a horizontal asymptote at y equals 0. Okay, but it's kind of only a half asymptote. Okay, so for when a is bigger than 1, a bigger than 1, then you have as x goes to minus infinity, y goes to 0. Okay, when a, I put 0, but I actually mean 1 there, sorry. When you're between 0 and 1, then you might get something different. Okay, so I'll leave that for you to fill in. So let's do this transformation one just so we get a handle of it. So this is 2 to the power x minus -2, okay, plus 1. So if I do the first one, it's with the x. Okay, so that's going to be 2 to the x minus -2. And this is going to be a shift left of 2 units. Okay, so the horizontal asymptote is going to be the same. Okay, but I'm just going to subtract 2 from each of my values up above. So instead of being at 0, 1, I'm going to be at -2, 1. Okay, and instead of 1, 2, I'm now at -1, 2. And instead of 2, 4, I'm at 0, 4. Okay, and then it's going to be 1, 8. Okay, and then over here, this is when I get the 1/2. So this is -3 and 1/2, okay, etc. And my graph is going to approach that asymptote, okay, and then grow very quickly this way. Okay, so I've shifted 2 units to the left, and then for the next step, I just add 1 to it. So here we shift up 1 unit. Okay, that will shift the asymptote. So it's now going to be at y equals 1 over here. And all of my points just go up 1. So it's -2, +2. -3 is at 1.5. So it's 3 over 2. -1 is going to be at 3. And 0, I'm going to be at 5. And then at 1, I'm going to be at 9. Okay, so it's the same shape again, but it's just been shifted up 1 unit. Okay, so for these exponential graphs, the transformations work the exact same way. You just want to be aware that when it happens inside here, in the exponent, okay, these shifts are the horizontal shifts. Okay, if there's a multiple on the x, then it's going to be the horizontal compression, expansion, etc. Okay, but they work the exact same way. Now, there's a special base, and I'm not going to go into this table very much, but there's a special base called Euler's number, or E. So E has to do with this 1 plus 1 over n to the power n. So this is just to show you that as your n's get bigger, that this is approaching some number. Okay, so that's what this table says. So this thing is approaching what we call E. Okay, so as I get closer. So it looks like it's approaching the number 2.71828, etc., etc., and that's what we call E. Okay, so it is that number. There's a button on your calculator, okay, so that you can compute it. So it's just like pi. It's an irrational number, so it's an infinite, non-repeating decimal. Okay, like I said, there's a button on your calculator to do it. So to find the value of E, you'd want to push that button, and it puts E to this little hat, and you'd have to enter a 1. So you have to give it the exponent. Okay, so what does this graph look like? So again, I'll do a table of values. Okay, so this is f of x equals e to the x. So when x is 0, it's 1. Okay, anything to the power 0 is 1. When x is 1, you get e, which is approximately 2.72, I guess. Okay, when you do 2, you get e squared, which is approximately 7.4. Okay, if we did negative 1, we get e to the minus 1, which is 1 over e, which is approximately 0.37. Okay, and similarly, if you do negative 2, you get e to the negative 2, which is 1 over e squared, which is approximately 0.14. Okay, so if we plot those, so at 1, we're at 2.7. Okay, at 2, we're at 7.4. Okay, so that's somewhere up here. Okay, and then down here, we're going down a bit faster. Okay, it's going to look the same. Okay, it has the same shape as 2 to the x. In fact, it's very similar. It lies in between 2 to the x and 3 to the x, since e is between 2 and 3. Okay, so that's what it looks like. Don't be afraid by the e. Okay, you still have this asymptote at y equals 0. It looks the same. Okay, so there's a button on your calculator to compute those values. Make sure you know how to do that. I'm going to leave this transformation for you. Okay, so transform that graph using the... So you're going to want to start with e to the x, which we just did. Then you're going to want to do e to the minus x, so you have to do that one first. And then you're going to take, e to the minus x and add 3 to it. Okay, so now, what about exponential equations? Okay, so this is part 1, because we can only solve some at this moment in time. So a to the u, if a to the u is equal to a to the v, because they're the same base, okay, so because they're the same base, we can conclude that the exponents have to in fact be equal. So then u must equal v. So we can use this idea to solve a number of exponential equations. So since the bases are both 2, okay, then we can conclude that the exponents have to be equal. So then this is true when x plus 4 equals x squared minus 2. Okay, so now I just want to solve this, and this we know how to solve. This is a quadratic, so let's move everything to the right. So it's going to be x squared minus x minus 6 equals 0, and then I can factor that. So it's going to be x minus 3 times x plus 2, which means that x is going to be 3 or x is going to be negative 2. Okay, so those are my solutions. Now let's check. So if I plug in x equals 3, then I have 2 to the 3 plus 4, okay, equals 2 to the 3 squared minus 2. So that says 2 to the 7 equals 2 to the 9 minus 2, which is also 2 to the 7. So that checks out. And if I do negative 2, then it's 2 to the negative 2 plus 4 is equal to 2 to the negative 2 squared minus 2. So that's 2 to the 2. And this over here on the right hand side is 2 to the 4 minus 2, which is obviously the same. Okay, 2 to the 2. So those are the only two x values where that equation is true. Now, for example 4 here, I don't have the same base. Okay, so I don't have the same base, so I cannot just say the exponents have to be equal. But I can turn these into the same base. Okay, so 4 is equal to 2 squared, and 8 is equal to 2 cubed. So I can replace those. So this is 2 squared to the x plus 6 is equal to 2 cubed to the 10. Okay, so that simplifies. So I multiply the exponents, so it's 2 times x plus 6, and this is going to be 2 to the 30. Now I have the same base. Okay, so now I can conclude that the exponents are equal. And then I can solve for x. So this is 2x plus 12 is equal to 30. Minus the 12, so 2x should be equal to 18, which means that x should be 9. Okay, and that's going to be my only solution for that one. Okay, I'm leaving 5 and 6 for you to do. Okay, so again, they're very similar to the ones we just did. So they're either going to be in the same base or not in the same base, but you're able to turn them into the same base. Okay, now this technique will not work on exponential equations like this, where you have 2 to the power x plus 1 equals 5 to the power 3x, because we cannot write 2 and 5 as the same with the same common base, or it's hard to. Okay, we can't nicely do it. So we need another technique to satisfy those, and that's why this is part 1. So we need another tool before we can do that. So that's going to come later in this chapter. Okay, so that's an introduction into exponential functions.